believe we are, right? All right. Well, good morning again. And let's cap what we did last time. The last thing we discussed yesterday was if we have a complex value, we said if we have lambda equal alpha plus or minus I beta. So I chose lambda equal alpha plus I beta, not minus I beta. And we wrote down the solution. And here we got this is the general solution where rho is the square root of alpha squared plus b squared. And we wrote the solution like that. Then we did an example, this one, and it turned out to be lambda equal to 1 plus minus I. So we took lambda equal 1 plus I, and when we chose theta, turned out to be tangent inverse alpha over beta, that is tangent inverse 1 will be pi over 4. So, and then we wrote down the solution, xn equals square root of 2 squared, that is rho. Sorry, this is to power n, that is a typo. And C1 cosine n pi over 4 plus C2 sine n pi over 4. And then if you evaluate x0 equal 1, x1 equal negative 2, you get C1 equal to 2, C2 equal minus 3. However, now if you take lambda equal 1 minus I, then this will be minus. So your angle alpha is positive and beta is negative. So your angle is this one. So theta is gonna be minus 1. That's gonna be minus pi over 4. So if you write down the solution, then you're gonna get minus C2 n pi over 4. And now if you evaluate x0 and x1 to obtain C1 and C2, you'll end up with minus 1 and plus 3. And so the solution will be the same. Okay? So it doesn't matter whether you take lambda equal alpha plus I beta or you take lambda equal alpha minus I beta. It doesn't really matter. Okay? All right. So this is the end of that section. Any questions so far? Okay. So now we're gonna move on to section 2.5, undetermined condition. So coefficient. All right. So basically what we're gonna look at xk, xn plus k plus xk minus 1, xn plus k minus 1 plus a1 x of n plus 1 plus a0 xn and equal to some function fn. And this is 2.5.1. Last time we called it 2.3.1. And then we're gonna look at the homogeneous one, ak xn plus k plus ak minus 1 xn plus k minus 1 plus a1 xn plus 1 plus a0 xn equals 0. So that is the homogeneous counterpart, 2.5.2. All right. So I'm going to define the operator L by AK EK plus AK minus 1 EK minus 1 plus A1 E plus A0 I. I is the identity map. Then Lx of n is AK EK plus AK minus 1 EK minus 1 plus A1E plus A0I applied to Xn. And then consequently, Lxn equals 0 gives 2.52, right? That is nothing but 2.52. And so Lx is f is 2.51 and Lx equals 0 is 2.5.2. Okay? So if xp is any particular solution of 2.51, then we're going to have Lxp equal f, correct? In addition, if z is any other solution of 2.51, then Lz equal f, correct? So you see what happened? Now let's take a look at Lxp minus z. That is Lxp minus Lz, and that is f minus f, that is equal 0. Okay. Any questions? So I'm gonna turn the this one here. Thus, xh equal xp minus z is a solution. And I'm gonna define this one as like that, is a solution of 2.51. Sorry, 2.52. Okay. Now, so the question is now, how do we determine? So we know XH. So we know how to find XH of 2.52 using the three cases of yesterday. Lecture. Okay? And then so now we need to learn how to find XP of 2.51. Okay? And then thirdly, the general solution of 2.51 is Z equal XH plus XP. Okay? Or XN equal XH of N plus XP of N. That is the solution of 2.51. All right. So the particular solution XP of 2.51 depends on the nature of Fn. Okay? Any questions so far? So let's do an example. So we're going to do a couple of examples today. I'm going to call it example 1. You can look in the book. Let's say we want to solve xn plus 2. We're going to concentrate on second order. Just to illustrate our point, we're going to concentrate on second order. Xn plus 1 sorry, plus minus 6xn equal 8. Okay. So let's take a look at finding xh of xn plus 2 plus xn plus 1 minus 6xn equals 0. So this is lambda squared plus lambda minus 6 equals 0. Okay. And you can see this factors into lambda plus 3, lambda minus 2 equals 0. So we got lambda 1 equal minus 3, lambda 2 equal 2. So this is a distinct root. Okay. So hence xh of n is c1 lambda 1 to the n plus c2 lambda 2 to the n, that is c1 minus 3 to power n plus c2 2 to power n. So we found xh based on what we learned yesterday. Now, for xp, since fn equal to 8 equal constant, we assume xp of the form xp equal a, where a is to be determined. Okay? Where a is a constant, is a parameter. So what we're gonna do is we're gonna substitute xp equal a into our main equation. And I mean this one. We're gonna substitute xp equal a into our main equation. So, well, xp is a does not depend on n, so this is a plus a minus 6a equal 8. Or minus 4a equal 8, or a is minus 2. Hence, xp of n is minus 2. Therefore, the solution is xn equal xh plus xp, where is xh is c1 minus 3 to the n plus c2 2 to the n plus xp minus 2. Okay, so that is our solution. Any questions? What do you think? All right, now we're gonna know, so I'm gonna say example 2, and I am only going to change, I'm only gonna change this one to 3 to power n. Because I don't want to solve the left-hand side all the time. All right, so we already know xh. Now, since fn equal to fn equal to 3 to power n, we take xp to be a times 3 to power n. You see what happened? And now substitute. So xp of n plus 1 is a times 3n plus 1. xp n plus 2 equal a 3n plus 2. You see what happened? Now go ahead and substitute xp here. Take 2 minutes. I need you to do some calculation on your own. Put xp in here and see if you can solve for a. You got a couple minutes. Then I'll be back to finish it for you. Sure, well, two more data. All right, there I am. So we're gonna have a times 3 to power n plus 2 plus a 3 to power n plus 1 minus 6 times 3 to power n, and that is 3 to power n from here. See what happened? I'm gonna factor. So this a times the 3 squared plus a times the 3 minus 6 to power 3 to power n equals 3 to power n. Divide by 3 to power n, you get 9a plus 3a. This is minus 6a. Minus 6a. Simplify by 3 to power n, that is equal to 1. Divide by 3 to power n. You see that? And any questions? So we have 6a equal 1, then a is 1 over 6. And so xp of n is 1 over 6 times 3 to power n. And the solution, xn, is xh plus xp. That is your xh here. You see it? Okay? Any questions? Are you digesting this? So it's basically like different method. Okay? Any questions? All right, let's do another example. So example 3, And now let's take 3 to the n plus 1. Okay? So we're going to get rid of this. And then you're going to take, this is a plus 1. So you're going to take xp is a to power 3n plus b. This for that and this one for that. Because 3 to the n and 1 are not compatible. So you have to have one parameter for each. One parameter for this, which is a times 3 to power n, and one parameter for 1, which will be plus b. And then okay, and then you substitute in there. So let's do this one. Why don't you go ahead and substitute and see what you get again? You see what happened? Because of the presence of 3 to power n plus 1. This and this are not compatible. Okay? So you have to have a parameter for each. So go ahead and substitute into the difference equation. All right. Let's xn plus 2 will be a 3n plus 2 plus b plus a 3n plus 1 plus b minus 6 xn minus 6 xn is a times 3 to power n plus b equal 3 to power n plus 1. You see what we did? Again, as we did before, let's factor 3 to the n out. Okay? And then I have plus, how many b's? I have 2 b's minus 6 b's minus 4 b equal 3 to power n plus 1. Note that this is 1 times 3 to power n plus 1. So what does that mean? The coefficient of 3 to the n equal to the coefficient of 3 to the n on either side. So I have this equal to that, and I have this equal to that, because constant equal constant, and coefficient of 3 to the n equal coefficient 3 to the n on either side. So I'll have 9a plus 3a minus 6a equal 1, and I have minus 4b equal 1. Okay? And here I have A is 1/6 and B is -1/4. So XP equal to 1/6 times 3 to power n minus 1/4. And then you add these two equations together. You add XH to XP to find the general solution. All right. Any questions? Okay, so now let's say, okay, I have 3 to the n plus 5 to power n plus 1. So can you write the general form of XP for me? Can you do XP? What do you think it looks like? Anybody want to say something?
Wouldn't you just add more variables for each term
Read it to me.
um, x of p would equal a 3 to the power n plus b 5 to the power n plus c.
Plus what?
B times 5 to the power n
Okay.
plus c.
Plus c. Correct. Again, this one and this one and this one, none of them is compatible, correct?
Yes.
So you got the idea now? Okay. All right. So let's all right. Let's take this out. And now let's do this one. 2 to power n. So what do you think is XP is? What is XP? Anybody? It's like this one before, right? Anybody want to take a guess? No one? All right, so let's assume it's A times 2 to power n. And let's plug in. So you will have A minus 2n plus 2 plus A minus 2n plus 1 minus 6 minus 2 to power n, that is 2 to power n. So let's factor 2 to the power n. So what do we have here? So we have this. So we got 4a plus 2a. Oh, this is, sorry, I keep making the mistake. Minus 6a. Minus 6a equal 1. Or 0 equal 1. Beautiful, isn't it? What do you think? Any input from you about to what happened?
Is that because on x of h there's a 2 of n?
Exactly. So basically, at the beginning, when we did example 1 through example 4, this is example 5 now. I kind of lied to you intentionally. So we fall into the same trap. I lied to you so you can understand. I said xp depends on the type fn is, the function f. Well, that was not 100% correct. So xp depends on the type of the function f, provided no term in f is present in xh, correct? Provided no term in fn is present or is a part of xh. If so, then what we have been doing is not right. Okay, so now, so from now on, you look at h. First, you look at f. It's 2 to power n, so you put a times 2 to power n. Are we on board with this? Now, you look back and you say, well, 2 to power n is a part of xh. In order to distinguish it, you hit it with n. You multiply it by n. And now it's going to work. Go ahead and do it. So that is your correct xp now. Okay? So if you put xp n plus 2 will be a n plus 2, 2n plus 2, plus a n plus 1, 2 to power n plus 1, minus 6 a and 2 to power n equal 2 to power n. Okay? Let's simplify this now. 2 to power n. Okay? So this is a n plus 2 times 2 squared plus a n plus 1 times 2 minus 6an times 2 to power n equal 1 times 2 to power n. Because 2 to power n can be written as 1. So you need to look for the coefficient. So what is this equal to now? That is 4a times n plus 2 plus 2a times n plus 1 minus 6an equal to 1. Well, let's do the work. That is 4na plus 8a plus 2na plus 2a minus 6na equal 1. So what cancels out now, guys? 4na plus 2na, 6na minus 6na, they wave goodbye. So now you are left with 10a equal 1, and a is 1 over 10. And so xp is 1 over 10 times n times 2 to power n. Okay? Or you may write it like n times 2 to power n over 10. So you see the idea now?
So if f of n has multiple terms that are in x of h, you would do like each term would have an n in front of it, and then each term that is in x of h would have an n in front of it, and then each term that is not in x of h would then not have an n in it.
How about this one? 2 to the n plus minus 3 to the n plus 4, no, plus 5 to power n. How about that? Is that what you're asking?
Yes.
So xp is gonna be a times 2 to power n plus b times minus 3 to power n plus c times 5 to power n. Now look back at xh. Minus 3 to power n is present multiplied by n. 2 to power n is present multiplied by n. 5 to power n is not, leave it alone. Okay? I think this is the answer to your question, I believe.
Yes, thank you.
All right, so that will be example 6 now. Okay, so we're gonna learn by examples today. All right. Now I am really deviating from my book, but that's okay. So let's change gears now and take something with exponential in it. Okay, or let me just do something here. Let's say this is n cubed. You see what happened? 7, example 7. So xp is gonna be, this is a polynomial of degree 3. So you need to catch the general polynomial of degree 3. So what is the general polynomial of degree 3? Is gonna be a n cubed plus b n squared plus cn plus d. You see that? Just because I have n cubed here. Okay? What if I have n cubed plus 1? Well, that's okay. This will be fine too, because this explain all this, okay? Because if you're gonna do n cubed this and then plus c1 and then plus c2, c1 plus c2 is d, okay? So that will be correct too. All right, any questions? And if you do not include all the polynomial of degree 3, the most general one, then you will get some contradiction like 0 equal 1, or 0 equal 5, or 2 equal 3. So you'll get a contradiction in your work. All right? Any questions? Okay. So let's now change the gear a little bit. So we're gonna get rid of all this. Let's say I have example 8, xn plus 2 plus 9xn equal to sine of 3n. Okay? Well, first of all, we need to find xh for xn plus 2 plus 9xn equals 0. That is lambda squared plus 9 equals 0, lambda equal plus or minus 3i. So that means alpha is 0 and beta is 3. This is a complex. Okay? So rho is 0 squared plus 3 squared, square root of 9, that is 3. And theta is tangent inverse alpha, beta over alpha, tangent inverse infinity, that is pi over 2. Because we know the tangent is not defined at pi over 2. Okay? All right. So that's beta over alpha. That's so the solution xh of n equal to, remember what the solution is going to be, rho to power n, 3 to power n, c1 cosine n pi over 2 plus c2 sine n pi over 2. So that is the xh. Now, for xp, now the function is sine 3n. None of it is here. Exactly sine 3n. So since none of it is here, we only worry about the sine 3n. So it's going to be a, I'm going to stick to my note, a sine 3n. Now you need to add any time you have a sine or cosine, not and. And is part of or here. Anytime you have sine or cosine term, you need to put both terms. Plus b cosine 3n. Okay? You see what happened? Now you need to look here. So you're going to have a sine 3n plus 6 plus b cosine 3n plus 6 plus 9xn plus 9a sine 3n plus 9b cosine 3n equal to minus 3n. So here you are going to use sine u plus v. Sine u plus v is sine u cosine v plus cosine u sine v. And we are going to use cosine u plus v, that is cosine u cosine v minus sine u sine v. Okay, you gotta use both. All right. So if you use everything together, and then you're gonna have, I'm gonna read it off my note. You're gonna have a cosine 6 plus 9a minus b sine 6 sine 3n plus a sine 6 plus b cosine 6 plus 9b cosine 3n, and the whole thing is equal to, this is sine 3n. Sine 3n. So you have this equal to 1. So this is equal to 1 times sine 3n plus 0 times cosine 3n. Why did I put cosine 0? Why did I put 0 times cosine 3n? Because look, the coefficient is sine 3n and the other coefficient is cosine 3n. So that means this is equal to 1 and this one here is equal to 0. You see that? And now you can solve for a and b. Okay? Now you solve for a and b and you'll get your answer. And this example is fully done in the book, so there is no question about it. So any question, first of all? So I'm gonna play the devil advocate here. Let's say here I have n squared sine 3n plus n cubed cosine 2n. So my question is, what is xp? The general form. This will take you 3 days to compute if you want to compute it. But I need the general form. All right. So for this one, xp is going to be a1n squared plus a2n plus a3 sine 3n. Do I stop here, guys? Forget about this term yet. Am I done with this term? What do you think?
No.
What do I still need? Which term? I need
Cosine.
the cosine part, right? Plus a4 n squared plus a5n plus a6 sine 3n. Now I'm only done with this. I need to do the n cube plus b1 n cube plus b2 n squared plus B3N plus B4 cosine 2N plus, I need the sine part of it, B5 N cube plus B6 N square plus B7N plus B8 times sine 2N. Now we are done. This is the worst case scenario, okay? All right? Any questions? I really don't want to do too much in this. Look here, I have a table, and on the table, I says table 2.1 shows how to find XP. But I make an exception. This is 62. I need you to understand. Oh, at the bottom of page 65, I say table 2.1 provide guidance on how to construct XP in the case that none of the terms present in XP are parts of the forcing function Fn. So they're not. Okay? And then you have a table, whatever you need to do, you can do. All right, any questions? I think I covered most of the things that you need to. Let's take a few minutes break and come back. 5 minutes. We'll stay recording. Hi, Let's go. Okay, any questions? Now, all right. Now we're gonna look at a different concept. So this is section 2.6, variation of parameters. Now, the coefficient AI, I equal 1 to K, may depend on N. You see, the method we did before, the coefficient are constant. So the method we just discussed today, the coefficient are constant in order for this to work. All right. So let's take a look at xn plus 2 plus p of n xn plus 1 plus q of n xn equal to fn. So that is 2.6.3. Okay. And let's take a look at, so P, Q, and F are defined on some set and not. Okay. All right. So the homogeneous equation is xn plus 2 plus pn xn, plus 1 plus qn xn equals 0. 2.63. 4. Okay. All right. Suppose the solution of 2.64 is xh of n equals c1 x1 of n plus c2 x2 of n. Okay. Now we assume a particular solution xp of 2.6.3 of the form xp of n equal u1 of n x1 of n plus u2 of n x2 of n, where u1 of n and u2 of n are need to be determined. Okay? They need to be determined. We assume the condition that delta of u1 of n times x1 of n plus 1 plus delta u2 of n x2 of n plus 1 is 0. So this is a very important, and actually it comes up naturally. This is 2.66. And that is 2.6.5. So you see the setup. I'll give you a minute to look at it. All right. Then we're gonna evaluate, we're gonna compute xp of n plus 1, and that is gonna be u1 of n plus 1, x1 of n plus 2, n plus 1, plus u2 of n plus 1, x2 of n plus 1. That's xp. Okay. And I am going to rewrite this as u1 of n, x1 of n plus 1, plus u2 of n, x2 of n plus 1, plus delta u1 of n, x1 of n plus 1, plus delta u2 of n, x2 of n plus 1. Now, this is 0 because of this condition. Okay? Now, any questions? So the same thing, I calculate xp of n plus 2, and I'm gonna get u1 of n, x1 of n plus 2, plus u2 of n, x2 of n plus 2, plus delta u1 of n, x1 of n plus 2, plus delta u2 of n, x2 of n plus 2. If you calculate xp of n plus 2. Now substitute xp of n, xp of n plus 1, and xp of n plus 2 into 2.6 point, we're gonna do it here, 2.6.3. And get del u1 of n, x1 of n plus 2, plus del u2 of n, x2 of n plus 2 equal fn. And remember what we have del u1 of n, x1 of n plus 1, plus del u2 of n, x2 of n plus 1 equals 0. That is this condition here, 2.6.6. That is condition 2.6.6. So we need to solve the system. To get del of u1 of n equal to minus x2 of n plus 1 fn over w of n plus 1 and delta u2 of n equal to x1 of n plus 1 fn over w of n plus 1. Now, what is w of n plus 1? W of n plus 1 is equal to the determinant x1 of n plus 1, x1 of n plus 2, x2 of n plus 1, x2 of n plus 2. This is a determinant. Okay? Remember, that is the delta difference of u1 of n, u2 of n. So we need to solve for u1 of n. So in other words, u1 of n equal to s equal n0 to n minus 1 minus x2 of s plus 1 f of s over w of s plus 1 and u2 of n s equal n naught to n minus 1 x1 of s plus 1 fs of w of s plus 1. And now remember what xp is u1 of n x1 of n plus u2 of n x2 of n. Now you know u1 from here, u2 from here, and you already know x1, x2 as the solution of the homogeneous equation, and you have the full solution. Okay? So you may look at a theorem. I summarize the whole result in theorem 2.61. So we summarize the result into this this one, and I think I'm gonna stop here. Next time I will do a detailed example on this one and move on. Okay. So are there any questions before I stop recording? There is a homework I assigned a couple days ago. I will assign a homework tomorrow. Any questions?
The homework you said that you assigned a couple days ago isn't on Canvas.
It's not?
No.
Oh, maybe I need to hit the publish, maybe. I will check. Okay. I will check. Maybe I forgot to hit publish. Are there any other questions? Okay, so let's see. No, there is homework 3 actually. Homework 2 you should be it's a past due already, right? So no, this is homework number 3. I may not have hit publish. It's very sensitive to that, which I will do. All right, I'm gonna stop recording. I have a meeting. Can I show Lily? Where is Lily? All right, you stay on. Hi, Lily. Come. Come say hi to the class. Let's go. Wait, we're gonna have a treat. Wait. Yeah, no, Lily, come back here. Come here. Here's Lily. I don't know what I'm doing. Here's Lily. Did you see? Say hi to the class. Yeah, there we go. I gotta stretch. I've been sleeping all day. All right, guys, I will see you tomorrow. We're gonna stop recording. Oops.